Now, if you put a small bismuth sample in, all the different frequencies are going to be shifted by roughly the same phase. So they'll all interfere at the same manner when they get here. And so just as in the forward wave theory, as you gradually add bismuth, the interferometer, you'll start to see it switch back and forth, because with a little phase shift, now they interfere such that the waves from the other detector are the ones that get here. And from this detector, they'll go the other way. So you'll see the switching just as the switching occurs back here. However, if you add enough bismuth, different ones of the frequencies will begin to shift by different phases. If you take the same total length out of waves that have different wavelengths, they're going to shift by different amounts of phase shift. If you put enough bismuth in so that the highest frequency wave shifts by one full wavelength more than the low frequency of all the waves that can make it through the interferometer, then you won't see the interference anymore. You'll have a uniform distribution of phase shifts everywhere between 0 and 360 degrees over the full bandwidth that goes through the interferometer. So in that case, the interference will disappear. Both detectors will then have roughly half of their waves going toward the source, so roughly half the particles will end up at each detector. Now, to compute when that condition occurs, let delta lambda be the width of the wavelengths accommodated by the interferometer. The interference will disappear when the number of wavelengths by which the waves are slowed down by the bismuth is equal to lambda over delta lambda. You have to have enough wavelengths so that the delta lambdas add up to one full lambda between the highest and the lowest frequencies. So the total distance by which the bismuth retards the waves is this n times lambda, which gives lambda squared over delta lambda. Now the momentum is given by P is h over lambda, and by simple differentiation, delta P is given by minus h delta lambda over lambda squared. So if you multiply the two together and take absolute values to ignore the minus sign, you get exactly the Heisenberg relationship. So the interference is going to disappear in the reverse wave theory at exactly the same relationship, exactly the same amount of bismuth as in quantum mechanics. Now, if one reduces the bandwidth from one of these detectors by inserting the analyzer crystal, so that the reverse waves from this detector now have a narrower width, only a smaller width of frequencies will go back through the interferometer, it's going to take more bismuth to wash out the interference that you'll see here. Because this relationship still holds, but you'll now have a narrower delta P. But in this theory, what you'll see is you'll see the signal in this detector go on and off. Because in the narrower bandwidth, even with more bismuth, because it's narrower, most of the different wavelengths will interfere in the same manner. So those wavelengths will all end up either going one way or the other way back here. If they go this way, you're going to see particles. If they go the other way, then you won't see any particles. So adding more bismuth after the crystal is put in will make the signal here go on and off. But in this theory, nothing is happening backwards in time. The frequency width here is narrowed before the waves go through the interferometer. The idea that the interference can be changed by narrowing the frequency width after the waves have already left the interferometer is completely illogical. The interference can only be affected by the narrowing if the narrowing occurs before the waves enter the interferometer. This experiment actually provides direct experimental proof that the waves go in the reverse direction. Again, in this reverse wave explanation, all the different wave frequencies act independently. So there's no mutual coherence to form a wave packet out of them. Each particle neutron at the source responds to the wave of, each particle neutron responds to only one of the waves in the frequency width. So each neutron has one and only one energy. There's no uncertainty in the energy of any one particle. Instead of a wave particle being in multiple states simultaneously, as in current theory, here one simply has multiple waves. Now there's some unpredictability, again, as to which of those waves the neutron source will respond to at any time. But just as in the double-slit example, this is readily explained in terms of unknown variables in the source of the neutrons. This is very much analogous to the double-slit. There the particle went through only one slit. Here the neutron will follow only one of the waves in this bandwidth. The waves in the double-slit went through both slits. Here, let's see. And the neutron here is in only one state. In the double slit, the waves went through both slits. Here, there are multiple waves. There are waves in all the different frequencies in the bandwidths. So it's very much an analogous situation. It's just that there are more states involved here than in the case of the double slit. So every object in this explanation has exactly one state. And yet one still can derive Heisenberg's relationship. So there are no inherent uncertainties. The whole wave packet uncertainty principle way of looking at things only arises in quantum mechanics because of the prior error of assuming the forward motion of the waves. With forward waves, one must view all the different wave frequencies as being mutually coherent, thus forming a wave packet. Without the wave packet, one can't explain why the interference disappears when you add enough bismuth, enough to make the packets no longer overlap. So the wave packet is one giant coherent wave, just as you had in the double-slit experiment. And because the wave is the particle, you're forced to conclude that the particle is in multiple states simultaneously, that its state is uncertain, just as you're forced in the double slit to conclude that the particle goes through both slits. Now, the fact that the uncertainties are unavoidable in the forward wave theory really should be understood as another refutation of the forward wave theory. To exist is to be something in particular. No real thing could be nothing in particular. So inherent uncertainties would constitute a contradiction and could not exist in real things.